Good day everyone. Today, I am going to discuss the properties of logarithmic functions. We will explore the key characteristics such as the product rule, quotient rule, power rule, base A of logarithmic A, logarithm of 1, and demonstrate their applications in simplifying expressions and solving equations. Before we proceed to our discussion, let me show and read to you first our objectives. So at the end of this lesson, the students will be able to recognize the common applications of the properties of logarithmic functions, solve logarithmic equations using the properties of logarithms, collaborate effectively with classmates to solve problems related to logarithmic functions. So, what does properties of logarithmic function mean? Basically, these are the rules and relationship that govern how logarithmic function behave. The properties of logarithms enable us to change the form of logarithmic statement so that the products can be converted to sums, quotient can be converted to differences, and powers can be converted into products. And now, let's explore these 5 properties of logarithmic functions. For x is greater than 0, y is greater than 0, a is greater than 0, a is not equal to 0, and any real number, the following properties hold. First, we have the power property. This property holds the description of logarithm of a number raised to a power is equal to the exponent multiplied by the logarithm of the number. Mathematically, this is expressed as log base a of x raised to r is equal to r times log base a of x, where a is the base of the logarithm, x is the number, and r is the power. We also have the quotient property that holds the description of logarithm of the quotient of two numbers is equal to the difference between the logarithms of the numerator and denominator. Mathematically, this is expressed as log base a of x over y is equal to log base a of x minus log base a of y. Next, we have the product property. The logarithm of the product of two numbers is equal to the sum of the logarithms of the individual factors. Mathematically, this is expressed as log base a of x times y is equal to log base a of x plus log base a of y. We also have the logarithm of 1, so this is mathematically expressed as log base a of 1 is equal to 0. This states that the logarithm of 1 to any base is always 0. Lastly, we have the base a of logarithm a. The base a of logarithm of a is 1. So meaning to say, any number raised to the power of 1 equals itself. And this is mathematically expressed as log base a of a is equal to 1. Now, let's move to the examples in solving logarithmic functions using its property. So first, we have the power property. The power property of logarithms states that log base a of x raised to r is equal to r times log base a of x. So in this case, we have log base 3 of 9 raised to 4. So applying the power property, we get log base 3 of 9 raised to 4 is equals to 4 times log base 3 of 9. So we all know that 9 is equals to 3 squared. So we can write the expression as log base 3 of 9 raised to 4 is equals to 4 times 2 times log base 3 of 3. So since log base a of a is equals to 1, we have log base 3 of 3 is equal to 1. Therefore, we have 4 times 2 times 1. And then the answer of our logarithmic expression of log base 3 of 9 raised to 4 is equals to 8. Next, we have the quotient property. The quotient property of logarithms states that log base a of x over y is equals to log base a of x minus log base a of y. So applying this to the given expression, we have log base 2 of 8 over 2 is equals to log base 2 of 8 minus log base 2 of 2. We know that 8 is equals to 2 cubed and 2 is equals to 2 raised to 1. Now we have log base 2 of 8 over 2 is equals to 3 minus 1. Therefore, our logarithmic expression of log base 2 of 8 over 2 is equals to 2. And now we have the product property of logarithms that states that log base a of x times y is equals to log base a of x plus log base a of y. So applying this to the given expression, we have log base 2 of 8 times 16 is equals to log base 2 of 8 plus log base 2 of 16. So we know that 8 is equals to 2 cubed and 16 is equals to 2 raised to 4. So substituting these values, we have log base 2 of 2 raised to 3 plus log base 2 of 2 raised to 4. So using the power property of logarithms, we have log base 2 of 8 times 16 is equals to 3 times log base 2 of 2 plus 4 times log base 3 of 2. So substituting, we have log base 2 of 8 times 16 is equals to 3 times 1 plus 4 times 1. Therefore, log base 2 of 8 times 16 is equals to 7. The example shown here in the logarithm of 1, we have log base 2 of 1 is equals to 0. This means that 2 raised to 0 is equal to 1. Log base 10 of 1 is equals to 0. This also means that 10 raised to 0 is equal to 1. And log base e of 1 is equals to 0. So this means that e raised to 0 is equals to 1. This is because any number except 0 raised to the power of 0 equals 1. The logarithm is essentially asking what exponent is needed to get 1. The answer is always 0. Lastly, we have the base a of logarithm a. So the example illustrates log base 2 of 2 is equals to 1. This means that 2 is raised to 1 equals 2. Log base 10 of 10 is equals to 1. This also means that 10 raised to 1 is equals to 10. This is because the logarithm asks, to what power must we raise the base to obtain the number itself? The answer is always 1 because any number raised to the power of 1 equals 1. So that ends our discussion of the properties of logarithmic functions. We've explored the key properties such as the product rule, the quotient rule, the power rule, and the special cases of the logarithm of 1 and the logarithm of the base itself. Understanding these properties is crucial for simplifying and manipulating logarithmic expressions, which are fundamental tools in various fields of mathematics and science. While we've covered several examples, the applications of these properties extend far beyond what we've discussed, offering a powerful framework for solving a wide range of problems. That's all. Thank you.